Hello, my name's Peter Laurie, and this talk is on using shared memory in Java. How do you go about doing this, and indeed, why would you even want to? We have a couple of libraries called Chronicle Queue and Chronicle Map, which make extensive use of a library called Chronicle Bytes, which is where our support for this functionality resides. And as you can see, you get a significant number of downloads, over 60,000 a month. And however, you can use shared memory directly yourself using plain Java. It is used by a significant proportion of all tier 1 banks and to access this kind of functionality. So why would you want to do this? Well, when you have a series of microservices that need to talk to each other, and they need then they can do this via any kind of messaging fabric, such as message bus, HTTP, TCP. There's a variety of means of doing this. However, if you use shared memory, then this is one of the fastest ways of passing data between processes, because it's all literally in memory, and you're accessing the same data, the same bytes from multiple processes at the same time. Now, added bonus to this is that if you use a memory map file, then that data is also persisted. It can be the size of your available disk space, so it's not limited by your heap size or even your main memory. It can actually be very large, so you've got access to a lot larger area of storage. And indeed, there is no broker involved in this situation. The only agent that is working on your behalf in the background is, in fact, the OS. So even if every process dies, but the OS keeps running, all of the data gets persisted to disk. Now, in the situation where the machine itself dies, we've got HA options available for creating redundant copies across machines. But in terms of using memory map files, you can do this all in one machine in open source. So one of the key things is that there's not only no broker involved that's going to add latency, but there's no system calls made on a per message basis. It's observable, so you can see every message, and it's stored in files which you can read from any process. It doesn't have to be running at the time. It can be run much later, and you can get latencies between processes, including serialization, that are around a microsecond or less. One of the things to note is that we're actually dealing at an extremely low level at this point. And in fact, we're dealing at the level where you're it's your L2 cache coherency bus, typically, that's involved in exchanging data between threads. So this is done on chip at the hardware level. And as you can see, you actually get a pattern of usage in terms of latency. So if you've got a dual socket Xeon, then everything on the same socket communicates fast. But you do see an added delay if you go from one socket to another. In the EPIC processes, they have call complexes. And within a call complex, you get very low latencies. In fact, you get even lower latencies because it's a small complex. But then between complexes, even on the same socket, you get higher latencies, and you get higher latencies again if you go between sockets. So certainly with AMD, you have to be much more aware of the internal structure of your CPU if you want to maximize performance and minimize latency. In terms of what can you get with real machines, so here's an example of the sort of latencies that you can achieve passing quarter of a kilobyte messages and 100 messages a second, which is a fairly good rate. And you can see that you get typical latencies that are around 400 nanoseconds, about 0.4 microseconds, or 2,500th of a millisecond. That's a typical latency. In the 3 nines, so the worst one in 1,000, That can be between 1 and 40 microseconds, depending on use case. It's interesting to see that the outliers on a virtual machine are as high as replicating data across different machines. So it is quite a high outlier if you're going to use a virtual machine. However, you can get the typical latencies can be just as good as bare metal. So it really depends on how sensitive you are to jitter as to whether using a virtual machine matters to you or not. For comparison, I've done some benchmarks on Kafka, and as you can see, at this rate, 100,000 messages a second, you're getting typical latencies that are at least around 3 orders of magnitude higher, if not more. So utilizing memory mapping has been available in Java since Java 1.4. It's fairly easy to do. You just create a mapping to the same file in multiple processes at the same time, and you're sharing them the same data. Now, one of the many disadvantages is that this is not actually thread safe. Another major disadvantage is that when Java 1.4 was created, having a assigned int as the size, which is up to not quite 2 gigabytes, then that seemed like a pretty good memory mapping size. But these days, limiting yourself to 2 gigabytes is something of a constraint. It would be much nicer to have to be able to map much larger regions, and certainly that's what our library does. You can use unsafe, which is a built-in class which you shouldn't use ideally, but sometimes it is still the best option compared to, say, using JNI to do the same thing. It's not only more performant than JNI, but it's actually probably less buggy than trying to write your own JNI to do it. So you can, there's a POSIX library that we produce that has things such as memory mapping and a lot of other low-level system calls that relate to files and memory. So it's another means of, and this will supports 64-bit long sizes. However, you can also use a library we have called MapBytes. What MapBytes does is it adds in things like thread safety, 63-bit sizes. It can also allocate data in chunks. So as the file, you can treat it as if it's a massive file, up to 128 terabytes. But in reality, it only allocates chunks of data as needed. Now, that's particularly useful on Windows and Mac OS, where sparse files aren't available. But on Linux, you can actually have a sparse file. You just create a huge region of half a terabyte or more, and then only the pages you actually touch to get turned into actual real memory or disk space. So another thing that Bytes adds is a number of complex operations, such as UTF-8, reading, writing UTF-8 strings that are object pulled, as well as support for data structures, enums, and so on. Now, Java has increasingly improved its support for off-heap memory, and one of the first ones of these is the Foreign Memory Access API, which had first appeared in Java 14. Note this is an incubator implementation. And in Java 15 has second incubator. Java 16 further iteration. Java 16 also introduced a library which is related, and it's called the Foreign Linker API, which allows you to directly interact with code that's written in C. And obviously that has a lot of crossover in usage. Java 17 has a further incubator iteration, and this adds a lot of the functionality that we need, but unfortunately it's still incubator. And in particular, if you use it, so there's Java 18 has a second incubator for it. Java 19 has fortunately now it's elevated itself to preview stage, which means that it's the final stage before actually being no longer incubator, no longer having an unstable API. And hopefully by the time we get to the next long-term support release, which is Java 21, we will see something that will help us migrate away from JNI and unsafe and a lot of other libraries which are used for binding to C libraries. And I highly recommend you have a look at this video. So here's an example of using memory mappings using the new API. One of the things to note is that this API doesn't actually compile in Java 19 because, as I mentioned, it's using an incubator library that can change APIs over time, which is why I look forward to the day it will become stable. Another thing which is takes a little bit of time to get your head around is that a lot of these parameters to these methods are all they're untyped, so you only know at runtime whether it's going to work or not, and it makes it difficult to work out what are all the valid combinations for these methods. That's partly deliberate to make so that the API doesn't become enormous like it could do if you were to go through every permutation that's valid. However, it does mean that it is a little bit of head scratching to find combinations that actually work, and like I said, those combinations are not the same between versions of Java either. So it's a little bit of a challenge. But what you may find interesting is that this is actually creating a memory region off heap on a file that's half a terabyte. So 512 shifted by 30 is half a terabyte. And that's a massive area of virtual memory. So it's only virtual. It's not actually using real memory, physical memory. It's not using disk either. So why would you do this? What use does it have? Well, the simplest use case we have for this kind of thing is in generating unique timestamps. And these are unique across an entire machine by default. So and the way that's coordinated is that we get a high resolution timestamp, like a nanosecond timestamp. And then we look at the most recent timestamp that anything on this machine has produced by looking in shared memory. And we ensure that it's greater than the previous value. We also embed in that a host ID so that we can actually have up to 100 different nodes producing unique timestamps across them without having to coordinate anything. So you'll only need to have a coordinated host ID, and then you can guarantee that every timestamp becomes a unique ID that can be used across many machines. So in the happy path, the time is greater than the previous time, and therefore it just returns it. However, if the time isn't greater, then it has to go through a loop. It finds the most recent time, it finds the next time that would be valid for that machine, and then tries that. And it just goes around and around in circles until eventually it's able to allocate a new timestamp. The way this looks is more natural than, say, UUID, because it is a timestamp, it's readable, it has the time in it down to a 1/10 of a microsecond resolution, but it also has a host ID embedded in there as well. So you can see just by reading a timestamp, which is reasonably natural to read, you can get a lot of information, and it's human readable. Not only that is that UUID is a very fast function all the same. However, it does create garbage, and it is still substantially slower. It's about 6 to 7 times slower than doing everything that I just mentioned. And at the same time, there's a good chance that you will also want a timestamp when you create a new event or a new request, so that you want to create a unique ID so you can make that request unique, but at the same time, you probably want a timestamp in there so that you know when it was created. So you haven't really saved very much. And so creating this sort of unique timestamp is a 2-for-1, and it's substantially faster. And it's able to do this because every timestamp on a given host uses shared memory to ensure that that timestamp will be unique and monotonically increasing. Now, in a more complex example, we use shared memory for storing our data in queues. So these are event stores, they're append only, and this is a dump of some of the housekeeping information that's associated with each queue. And you can see that there's a string key and a long value associated with it down the screen. And those longs can be used for storing information like locks and working out what the most recent roll cycles are and how much what its mod count is. So that is all done in shared memory, and we've got tooling that will allow you to dump out this binary format as YAML. You can also do the reverse so that it's easy to read as well and to manipulate and test. So we have a working example of this, which is open source. Everything I've mentioned to do with Q is all open source and Apache 2, so you can try it out yourself. So in this demo, we're looking at how do we create, how do we test these microservices that are using shared memory for passing data between them. So what we don't, one of the challenges of using really low level interaction with memory or off heap is how do you test it? How do you debug it? When something goes wrong, how do you see what's going on? And the way we deal with that is to create a much higher level interface, which is where you would be naturally working to do with events coming in and out. And so you're not dealing with the low level bytes unless you really need to. You can go down to that level, but for the most part, to start with, you should focus on the business logic and do behavior-driven development first for your event-driven system. And then you can go down to the bytes and try and get out every nanosecond where it makes sense to spend your time doing that. Obviously, the more you tune it, the harder it is to maintain. So there's a trade-off there. And certainly at the start of a project, you actually want to focus on flexibility, easy to maintain, so you can do rapid prototyping and iterative development cycles. And then as the product matures and you have called confidence that the DTOs aren't going to change very much, the events are not going to change very much, then you can look at micro-tuning them to try and get the best possible performance for what you've established as a realistic use case. So what does it look like? Well, in this case, we do still favor right from the start trying to use primitives where possible. So things like the timestamps are typically stored as primitives. In this case, it's a microsecond timestamp. There's a symbol, which is the which will be the instrument's name, like what are we trying to trade here? This is an example of a trade. But you can also see that we've got some enums and a string in there. You can have other data types, but where possible, we tend to try and use primitives. And so in this trivial example, we've got a microservice that expects one type of event in and it produces one type of event out, which is an execution report. So from the order, we build an execution report object. And when you're testing this is all in YAML. So we're dealing at this level where you can see the data structure. We've got an event in and an event out. And the main point to take away from this is that even though when it's stored in memory, even though when it's written and shared between processes, it's highly optimized, it's very much down at the binary level. When you're testing it and you're thinking about what business functions are we going to perform here, it is at a much higher level, and that's where you want to be describing the functionality or business component we'll implement. So what happens when the test fails? How easy is it to see when something's gone wrong? So if you were dealing with it at the binary level, you would just see that one of the bytes is wrong, and that would make it, that could potentially be very hard to diagnose, and you could waste a lot of time going through all the things that could possibly be. But at this level, because we're doing, we're working in YAML, we're doing a text-based comparison. So we expected a particular kind of event execution report. We got a different kind of execution report. So in this case, it's very easy to see that the order type is not the expected one. And then you can decide what action to take. Is the code incorrect? Is that the test should have been updated, like you've actually changed the input and you want the output to change as well, and that wasn't done. But you can very quickly diagnose what you need to do. And to fix it, say for example, it's only the output that is wrong, you can just copy and paste the actual over the expected, because the expected is in a file of its own, and you've updated the test if that's the appropriate correction. So we use YAML for data-driven tests. It's all based around behavior-driven development to ensure that we're specifying the requirements at a level that the business users could understand, using their language and their terminology. But we can go down to low-level performance considerations by using binary formats, pre-generated serialization code, and at the lowest level, we can use trivially copyable objects where it's effectively much like a mem copy, and there's very little serialization logic actually going on, and that can get well under half a microsecond end to end. So that's from when you want to write an event to when that event is actually called in another process, including serialization, writing to the file, writing to memory, deserialization, decoding the event type, and making the method call. Now, Chronicle Software is actively hiring at the moment, so if you're interested, please reach out to us. Otherwise, you can have a look at our website. And as I mentioned, all the code is on GitHub under OpenHFT. Thank you very much for listening.
That was a really interesting presentation. I like that.
Okay, thank you.
Yeah, I'm just looking to see if there's any questions on the Q&A thing, but I can't see any at the moment. So I'll just ask you a couple of questions that I can think of. So yeah, of course, Project Panama is one of those things that we've been waiting for a long time, as you said. And I think it will be very valuable when we actually get to the point where we can use it without having to enable preview features or incubator modules. Took me a while to figure out why they changed it from being an incubator module to being a preview feature.
I have a feeling that it's to show progression.
Yes.
To encourage people that it's coming soon. I don't think there's any limitations on how long it should be preview. I'm assuming it won't go back to incubator, but
no, I need to check, because I think the reason is that when it's an incubator module, it's not in the Java SE space. And
right.
when they move it to a preview, it actually falls into the Java SE space. So I think it's because of whether it's in the Java or JavaX namespace. I think that's what they've changed. But
it's still in the incubator package name.
Right.
So yeah, I feel a lot more confident when that disappears from the package name. Obviously, what I would like to see is obviously some backports. Unfortunately, I have a lot of clients that are still on Java 8. So yes,
I'll have to take that up with our engineering team, see whether we can do a backport to Zulu 8.
Yeah, I mean, the thing is, in reality, we only need a very small subset. So actually, that's the only bit that we would need backported, if you see what I mean.
Right.
Whereas perhaps backporting the entire thing isn't perhaps so practical.
Yeah.
There's a lot of features in there that are really cool, but because they weren't in unsafe, we obviously didn't use them.
Yes.
Yeah,
unsafe.
Yes, I think we'd have to come up with some sort of compatibility library, which we kind of have done. Another approach is to consider, I mean, we've talked about doing a rewrite from a newer version. So we might consider just doing a rewrite for version 21, assuming that's got it in there, and then do a proper version 21 native implementation of everything. And just effectively fork our libraries for the people who want the older version or the newer version.
Yeah, I can't see why it wouldn't be full featuring by Java 21, because what have we got, like 19? Okay, it's still going to be a preview feature, but I would expect 20 or the last one, 21. It'll definitely be a full feature, because I know they are trying to get Panama done and dusted.
That'd be good, because otherwise, I mean, they can always extend it later. Certainly from my own selfish needs, I only need a fairly small subset of what they need. So if they end up constraining it just to get it in, I'd be more than happy with that.
Yes. Yeah. Okay. I can't see any questions from the audience. So I guess I'm sure people can reach out to you if they have questions later. But
yes, please do.
Other than that, thank you very much. That was a great presentation.
Thank you, Simon.
Great. Thanks a lot.
Cheers.
Okay. Bye.